Welcome to Dynamics. This lecture is specifically about kinematics of rigid body. The question gives us 3 bars, and then the bar is CD, the other bar BC, and then bar AB. So the question, what it gives us omega CD, which is angular velocity of bar CD, and alpha CD, and ask us to find omega AB and alpha AB. So how we want to go and then do those calculations? So first of all, by looking into this problem, we need to know what types of motion each of them they have. We already know that bar CD has rotation about fixed point. That's the same for, so this is actually rotate about point D. And then for bar AB, this is rotation about fixed point, which is point A. Bar BC, that's just a general motion. So we just need to identify them before we go ahead with the problem. Now, if I proceed from point D to point C, again, the problem has two parts. One, calculation of omega, the other one, calculation of alpha. So let's just consider bar CD. If you look into bar CD, okay, this is the rotation about fixed point, that's point D, 60-degree angle here. Then I'm sure the direction of velocity at C is going to be something look like this. So it's going to be perpendicular to the radius. And in this case, the radius is 1.5 feet. So I can simply say velocity at C is equal to 1.5 omega, right? We already know that. Velocity is equal to R omega. This is the case where we have rotation about fixed point. So which would be velocity of C is 1.5 omega CD is given to us as 2. And the answer for this one is going to be 3 feet per second. So we know velocity at C, then we can actually start moving on from there. So velocity at C is given to us. We want to find velocity at B. So in such cases, we can use actually the center for zero velocity, and then the calculation for center for zero velocity is you just draw the bar BC, and then in the bar BC, once we draw it, we know the direction of velocity at C is look like this, and then the velocity at B is perpendicular to this line down here. So that's how velocity at B look like. So velocity at B is going to go right here, something like this. The angle here is 45. This is going to be 45, and that's going to be 45. And the angle here is 30 degrees. In order to find center for zero velocity, we know that every rigid body diagram or every rigid body object has instantaneous center for rotation. So at this moment, we can say actually this object rotates about a center. So in order to find that center, you go perpendicular to velocity. That's 2 location. So, and then that's what we have. This is perpendicular here, and this is perpendicular to the velocity. This is 30 degree, so that will be 60 degree. Easy. This is 45, that's 90, that makes this 45. And then we have 60 and 45. The summation needs to add up at 180, so this will be 75 degrees. Now I'm going to call this one IC, which is instantaneous center for rotation, or whatever other name you want to call it. Now from here, from this rotation to point C, I'm going to call this one RC, radius for C. The other one I'm going to call it radius for B. And this object actually rotates with omega BC. So let's simplify our calculation. We can say velocity at B is equal to RB omega BC, and then velocity at C is equal to RC omega BC. Now we know VC, we know RC, we can actually find omega BC. Once we found omega BC, we can just put it here to find velocity at B. But how can we find RB and RC? You have to look at this triangle. Let me just highlight the triangle. So if you look into the highlighted triangle, I can use law of sine because I know the angles and I know one side down here is 2 feet. Sorry, my OK Google thought I just called him. He didn't call OK Google. So now the law of sine is going to be, so you just look in every angle with every side. Again, if you don't remember law of sine was like this: sine of A over A is equal to sine of B over B is equal to sine of C over C in a triangle, such that if this is A, B, C, this side is C, this side is A, and this side is B. I'm going to use this equation in this triangle. So in this triangle, I have 2 feet. That's the side, and then I have 75 degrees. So sine of 75 degrees over 2 is equal to sine of 60 degrees over RB is equal to sine of 45 degrees over RC. Now you can cross multiply these relationships and then you can solve for RB and RC. If, for instance, if you solve for RB, you can say RB is equal to 2 sine 60 divided by sine 75. Remember, I'm doing cross multiply. Now from here, I'm going to get RB is equal to 1.79 meter and RC is equal to 1.46. So let's use these two numbers into the relationship that we have here. So I'm going to grab the number from here and then bring it here, and then the other number, bring it there. So I'm going to get velocity of C, we already have it. So we have 3 feet is equal to RC, which is 1.46 feet per second. This is feet, and then we're looking for omega times omega BC. From this relationship, you can find omega BC is equal to, so 3 divided by 1.46, and this is going to give me 2.05 radian per second. If you use this number into the relationship up there, from there you can say velocity of B is equal to RB, which was 1.79 into 2.05, and the answer for this is 3.66. That's easy. So far we know velocity of B, we know omega BC. Now if you move on to B down here, so in the other bar, you can see in the other bar you have something look like this, and that's how was velocity of B, which is equal to 3.66. Now the angle here is 45 degrees. The length of that was 2.5 feet. Now I want to find omega AB. So from this relationship, I'm going to say omega AB. Remember that VB is equal to RB omega AB. And then omega AB will be 3.66 divided by 2.5, and then this is going to be ended up as 1.46 radian per second. So we are lucky that we found the solution for the first part of this problem. The second part talks about alpha and then how we need to go about that, how we need to find alpha. There are two ways to solve that. One way is the way of what we call it, the method of scalar. The other one is the method of the vector. So I'm going to use the vector approach, but again, is the same problem can be done using the scalar approach. So let me just to copy the problem again. Okay, copy this down here. Okay, so in this case, I know the acceleration of d, which is 0. Okay, because point D is the point that doesn't move. Acceleration of A is 0 as well. So let me just to write the generic equation for acceleration, then we can actually specialize it for our case. We know that acceleration of point B is equal to acceleration of point A plus 2 terms, right? If I want to find acceleration of point B in terms of point A, plus 2 terms. The first term actually is the term for tangential, and the second term is about, so the first term is tangential, which is alpha cross with r. The next one is for normal acceleration, which is r omega squared. And remember, this relationship here, this is a omega is a scalar, but r is simply r. rb with respect to a, rb with respect to a, and then omega is omega of ab. Same thing here, alpha of ab. So I can repeat the same equation from C to D. So I can say acceleration of C is equal to acceleration of D plus alpha of CD cross with RC with respect to D, and then go ahead from there, minus RC with respect to D times omega square AB. So you can actually do it the other way, it doesn't matter, but this is a scalar. So in this case, this is a vector, vector, but this is scalar. So RC with respect to D times omega of CD. So let's use this relationship. In this relationship, this is 0. Now alpha of CD is, both of them are going counterclockwise. So I can say both of them are positive. So now in this case, alpha of CD is rotates with 5, but these are 5k. Remember that alpha and omega, they are in the Z. So alpha of CD is equal to 5k and omega of CD is equal to 2k. In this relationship, you can say acceleration of A is equal to RC with respect to D. So if you go, I'm sorry, in this relationship, I want to find, RC with respect to D. Meaning that if you go from point D to point C, how much you have the change in coordinate. So just look into something look like this, like a shape like this. If your coordinate is here, your origin is point D, right? And then you want to go from D to C. 1.5, angle here is 60 degrees. Now, I want to go, in this case, I want to go from point D to point C, meaning that I need to go how much up? I need to go 1.5 sine 60 up, 1.5 cosine 60 on the x, right? But that's on the x is negative. So I can say RC with respect to D is equal to, the value for this is simply 0.75. The value for this is 1.3. So I can say minus 0.75 I plus 1.3 in J. That's simple. So now I can just use that relationship and then do the rest of calculation. Acceleration of, so alpha is given to us, so it's going to be 0 plus alpha was 5k, so I have 5k cross multiply with RC with respect to D. In this case is minus 0.75 I plus 1.3 j. And last one is minus 0.75 I plus 1.3 j into omega square. Omega square is 2 to the power of 2, which is going to be 4. Remember, we don't use the k in this case because all we need, whatever we need, we have it. So we don't need to be worried about that. I need to find k cross I, and I need to find k cross j. In order to find I, j, k, just remember this little diagram, right? This is I, j, k. If you go counterclockwise, it's positive. When you go clockwise, it becomes negative. So I want to go from k to I. So I want to go from k to I. So k to I, the answer is going to be positive j. The other one, I'm going to go from k to j. So you see, the counterclockwise, now I'm going the opposite way, like this. Because I'm going the opposite way, I have to consider it negative. So this will be negative I. That's simple. So let's simplify this. I'm going to get acceleration of AC is equal to, so 5 times 0.75, you multiply by that, and then you're going to get minus 3.75 j minus 6.5 I plus 3i. The 3i is coming from here, 0.75 times this. And last one is minus 5.2 j. If you continue, you're going to get minus 3.5 I minus 8.95 j. So we found acceleration of point C. Now I want to find acceleration of point B. So if you want to go from point B to point C, the picture is going to look like this, right? So acceleration of C, we know it. We want to find acceleration of B. So RB with respect to C, if you go from point C to point B, we could say B with respect to C. Now I'm going to go negative 2. So it will be negative 2 in the I. That's it. There's nothing else. And then we already have some components. Let's go ahead and then write this equation. So acceleration of B is equal to acceleration of C plus alpha of BC cross with RB with respect to C minus RB with respect to C times omega BC to the power of 2. AB, I don't know. And then I want to find AC, that I already have it. AC is here. Alpha BC, we don't know this one either. RB with respect to C, we know it. And then we know this one. And omega BC, we know it. So let's go ahead and then do some calculation. Acceleration of B will be ABX I plus ABYJ, we don't know what they are, is equal to minus 3.5 I minus 195 J. Alpha of BC, that I don't know, but I know is in K, right? I know because we are in 2D. The alpha is always on the K. So K cross with minus 3.5 I minus 8.95 J. And lastly is minus the same R that we already have it. 3.5 I. So it looks like I'm creating a mess. This is not the R. RB with respect to C is given to here was just simply minus 2I. So minus 2I minus 2I omega BC. So I'm going to go scroll up here to see how much I found for omega BC. And then I'm going to put it in. Omega BC, we found it at 2.05. So 2.05 to the power of 2. So if you simplify this equation, again, K cross I, The answer is simply J. In this, you just have I here, we can simplify. So if I simplify the equation, that's what I'm going to get. I'm going to get so I'm going to get ABXI plus ABYJ on the I. I'm going to factor the I. I have a 3.5 here and I have another I here, right? So if you add these two I's together, you can actually find how much we have on the I. So for I, we have 3.5 I minus 8. That actually was for AC. What I could do, I could just jump into the latest part. So in each side, I have I in this side and I have J in this side. So in both sides, I have I and J. So what I'm going to say I in the left side has to be the same as I on the right side, or their coefficient should be the same. So the coefficient of I in the right side is going to be ABX, which is equal to, on the right I have minus 3.5 plus 2.05 to the power of 2 times 2. For ABY, for J I have ABY here, then I have minus 8.95, then I have a 2 here, which is minus 2 alpha of BC. We are lucky. So in this equation, we found alpha, we already found ABX. So if you simplify this, you can say ABAX is equal to 4.5 radian per second square. So we found, it's meter per second square. My bad. So the next one is, so we already know this. We already know ABY with respect to alpha BC. That's one relationship we have. Let's go to the beam AB. So beam AB was look like this, right? To the bar AB. It was rotating about point A. This was point B. So RB in this case, we can find RB with respect to A. So I can say RB with respect to A is equal to, the length of that was 2.5, which is going to be, again, 2.5 cosine, you go up, and 2.5 sine. So it will be 2.5 cosine 45, 2.5 sine 45. So we can say RB with respect to A is equal to 2.5 cosine 45, which is 1.77 I plus 1.77 J. So that's one thing I found. The other thing that I found is the relationship that I just showed you up there, that acceleration of B is equal to acceleration of A plus alpha AB cross with RB with respect to A minus RB with respect to A into omega of AB to the power of 2. We know acceleration of A is 0. Then alpha of AB we don't know. We know this is in K, right? RB with respect to A, I already know it. And then omega of AB we already calculated somewhere up there. And then we found for omega AB, yeah, somewhere here, omega AB was 1.46. So this is 1.46 radian per second. Let's just substitute in this relationship. In this relationship, you can say ABXI plus ABYJ is equal to alpha AB, that I don't know, but I know is already in K, right? So this is going to be 0 plus alpha AB in the K cross with RB with respect to A. RB with respect to A is 1.77 J minus 1.77 I minus 1.77 J into omega AB to the power of 2, which will be 1.46 to the power of 2. So we are good to go. We just need to simplify this equation. But in this equation, I already know ABX, right? ABX, I already know it on the I. So K cross I is what? K cross I is J. And then K cross J is minus I. I just proved it up there. If I simplify the equation, let's see what we have for the I on the right. On the right side, I have ABX. I already know that ABX was 4.5. So I can say I is equal to I and J is equal to J. For I on the right, I have ABX, which is 4.5. And then for I have this component, which is going to be 1.77 times alpha. So I have minus 1.77 alpha AB. What did I have for I? I have this component times this, right? So I have minus 1.77 into 1.46 to the power of 2. Now, if you simplify this relationship, you're going to get, in this side, you're going to get, this is going to be 3.77. 3.77. Now from this, that's 4.5. So you can say alpha minus 1.77 alpha AB is equal to 4.5 plus 3.77. From here, you can actually find alpha AB is equal to 4.67. So the method that we used was a vector approach to calculate the acceleration of AB, and we are done with the problem, because and then I don't need to do the sum of J, because is not anything off of my interest. The question only asked me to find alpha of AB. Thank you very much for listening to this video, and I'm going to put the link to the note on the bottom of the video, so you can actually